Hello and welcome back to Paleocast. My name is Dave Marshall and this is episode 119 on the Soom Shale with Professor Sarah Gabbott of the University of Leicester. Today we're continuing our impromptu series on South Africa, with this episode looking at the unique taphonomy of the Soom Shale biota. What are some of the fossils that we find here? What makes them so special? And how did they come to be preserved in the first place? Following this episode, we'll probably need to take a break from South Africa for a while, but if you have any other suggestions of different countries or lagerstätte, these sites of special preservation or concentration of fossils, please do let us know in the comments. We really do read them all. As always, you'll find images to accompany this interview on our website, and anything you can do to help get the show to new audiences would be most appreciated. So, for Christmas, I'd love a social media share from each and every one of you, and in return, I'll make sure that 2021 is filled with more fantastic paleo episodes with the world's best researchers. Hi Sarah, thank you so much for being on the show today.
You're welcome. It's very nice to be here.
Right, we always like to get to know you a little bit first and get to understand how you got to where you are today. So what was your route into paleontology?
I guess my route into paleontology perhaps wasn't a traditional one. Many people think of paleontologists as, starting as kids with amazing fossil collections and being, obsessed with dinosaurs and so on. But that wasn't me, actually. I grew up in a town just outside of London, and we didn't really have any rocks, and we certainly didn't have any fossils. So I kind of knew about dinosaurs, but that was pretty much it. I guess my routine really started because I loved animals, as simple as that. So I'd read about all different animals, and I love watching David Attenborough on the TV and all that kind of stuff. And this love of biology pretty much stayed with me throughout school. And then I came to pick my A-levels, and so obviously I picked biology, and I picked chemistry as well, and I picked physics. But 2 weeks into doing my A-levels, I absolutely hated physics. I couldn't get on with it at all. My maths wasn't really up to it, if I'm honest. So I was kind of rooting around for another A-level. And a school down the road did geology, so I thought, that sounds pretty good. So I went for that, and I never looked back really. So I did geology A-level along with the other two, and I absolutely loved it from the moment I took it up. So obviously I applied to go to university, and I got into Southampton and did a geology degree. And the whole time I was there, I was very attracted to paleontology, obviously, because it's about the biology of dead things. And that, I guess, is my route into paleontology.
Yeah, it's pretty similar to mine, I guess. So, hey, maybe I'll be professor one day. What would you be doing, though, if you weren't a paleontologist?
Yeah, I think that's a really interesting question. If I was growing up now, I would want to be, when I grew up, a footballer, if I'm honest. So I spent a lot of my childhood playing football down the park. But when I was a kid, women's football wasn't really a thing. It certainly wasn't an option. So that's what I'd be doing. That's what I'd be dreaming of if I was like 6 or 7 now. But now, as my adult self, I often think this question, particularly when I'm doing university administration and wondering what else I could be doing. And I think I'll probably do something around conservation, so conservation biology, maybe some sort of education and outreach, so I guess not dissimilar to something that you're doing now. But that kind of area is probably what I'd be doing, or I'd be a gardener.
Okay. It's probably one of the most unique answers we've had. Footballer. Dare I ask who you support?
Well, I support, obviously, I've lived in Leicester now for more than half my life. So I support Leicester City.
And you must have been very happy when they won the Premier League a few years ago then.
Yeah, it was absolutely amazing. And to be in Leicester at that time, honestly, I'll never forget it. I mean, people were coming out of their doors, their front doors, kind of partying on the streets. It was crazy. There were horns blowing all the time, and it was a great time to be in Leicester. And then when they came back and paraded the cup, and there was the free concert and everything, it was amazing. The whole city came out. It was great.
And for a bit of context because most of our listeners aren't in the UK, Leicester were pretty much the worst team in the whole league, and then they finished in like the last position they could be in pretty much. And then the next season, they just won everything. Yeah. It was unbelievable.
Yeah.
I am currently presenting from a little place called Old Trafford. You may have heard of it. So you can tell who I support. But anyway, that's enough football.
I have to say, I do follow the football, but I'm not a rabid football supporter, but I do really follow it, yeah.
Right. Taphonomy. What is taphonomy? How did you become a taphonomist?
Yeah, so taphonomy is a word which is a fairly long word, but actually it encapsulates an awful lot. So archaeologists use this term, paleontologists use this term. And what it really means is all the processes between the death of an animal through to it being discovered as a fossil. So all the processes that can occur to that carcass all the way through to it, being converted into a fossil and then being found. So, I mean, there's lots and lots to this, but, as an example, something dies. So you have to think about the way it reaches the place where it's going to become a fossil. So how is it transported? Does it sink fast? Does it sink slow? How is it buried by the sediment? Once it's in that place, does it get munched on by other creatures? Is it scavenged? Is it attacked by bacteria and decayed? Which tissues and anatomical features last, which don't? And how do those organic materials and the inorganic materials as well, the mineralized materials, how do they transform into materials that are going to be stable over geological timescales? And therefore, kind of how does it convert into a fossil? And all of those aspects really encapsulate taphonomy. And your second part to your question, how did I become a taphonomist? Completely by chance. So I really lucked out by getting a PhD on the Soom Shale. I was incredibly fortunate in that sense. And when I started to look at the fossils, there were some really interesting features, particularly on conodonts, which I guess we'll come on to talk about later. And I wanted to look at them in more detail. So I stuck the fossil under the scanning electron microscope, which allows you to see details of the anatomy in incredible magnification. So times 50, times 1,000, times 5,000, and upwards from there. And it also... the SEM, as we call it, also allows you to analyse the material. And when I did this, all this material was made of clay minerals, and the material I was looking at were muscle fibres. So it was really weird, because how do muscle fibres from a vertebrate that was swimming around, over 400 million years ago, how come now they're composed of clay minerals? And so this was a bit of a conundrum. We knew at the time that muscle tissues, muscle fibres could be replaced by the mineral apatite, so calcium phosphate. But at that point anyway, nobody had found that clay minerals could do this as well. So this kind of got me scratching my head and thinking about the taphonomy. So what had basically made this fossil? And that's how I got into taphonomy. And with this particular deposit, the more I looked, the more weird it became in terms of the taphonomy.
Right. Well, we'll unpack all of that throughout the rest of this episode. But I just want to get a sense of, does taphonomy affect every single fossil? Like every single fossil that we find, we have to consider its taphonomy? What's happened to it?
I think so, yes. So if you just stop and think about what we're trying to do as paleontologists is read the fossil record. And in that reading, the record that we look at isn't like the record that a biologist looks at. These animals are not moving around still, they're dead. And in almost all cases, something has happened to them. I mean, if you take, for example, probably the best preserved fossils in the world are insects in amber or other things in amber. But even they are slightly modified and changed by what's happened to them, by the fact that they've been encapsulated with this amber. But most of us, or a lot of us, particularly the fossils that I look at, are basically in sediments. And I spend a lot of my time looking at fossils which comprise the soft tissues of animals, so the bits that usually decay away. And when you're looking at that kind of fossil, taphonomy is critical. So in particular decay, we try and understand what tissues look like after various intervals of decay, because they don't look the same as they did in life. And we also try and work out, how decay affects where that fossil would sit on the tree of life when we interpret the anatomy.
Yeah, it sounds pretty important then. So, our case study, we're going to be looking at the Soom Shale that you said that you'd been studying. So, can you tell us about it as a fossil site? So, where is it, and how and when were its fossils first discovered?
Yeah, so the Soom Shale is a deposit in South Africa in the Cape Province. So if you go to Cape Town and you were to drive about 250 kilometres north of Cape Town, you reach this really gorgeous wilderness called the Cederberg Mountains. And the Soom Shale outcrops in this area, the Cederberg Mountains. So that's where it is. The fossils were discovered in about 1983. So my colleague and former supervisor, Dr. Hannes Teron, he used to work for the Geological Survey of South Africa, and he was looking in the shales of the Soom Shale for some fossils because the sequence of rocks the Soom Shale is in is something like 3,000 metres of sandstones, ranging from the sort of top from the Cambrian to the Devonian. So if you imagine the side of Table Mountain, that's all this sequence of rocks. And there were basically no fossils in this massive sequence of rocks to help them date the rocks. So they were looking in the shales because, as every paleontologist knows, shales are good places to go and try and find fossils. And they did. They found these kind of small, spiky, so about a centimetre long, sort of spiky clusters of things. And these were the first fossils. Now, when they were first written up, they were published as being the earliest vascular land plants. But Hannes was never really happy with that interpretation. And he managed to get these fossils to eventually my other supervisor, Professor Dick Aldridge, who was a conodont expert, and he was able to identify these fossils as conodonts. And the study of the Soom Shale really took off from that point then.
So if we were to go with you on a little field trip right now to the Soom Shale, what would the site look like? Is it just one place, or does this rock stretch out for hundreds of kilometres? And is it still being worked? Are people still collecting fossils there?
Yeah, so if you were to come with me, there are several sites where you can find fossils of the Soom Shale. So basically, what we do is we drive around, and it's all sandstone around there. But because the Soom Shale and the kind of little unit just above it are the only shales, you can see it from miles away because it's the only kind of shallow slope in the mountains, and the rest is really rough sandstone. And we dig it generally on farming land. So the Cederberg is famous for, it's got the highest vineyards, by the way, in South Africa. And lucky for us, one of the localities where we collect some of the best fossils is on this particular vineyard, which is brilliant.
Sounds good, yeah.
So we get to know the farmers very well there, as you can imagine. And generally speaking, I think, nearly all the locations are on farms. The other famous one is a place called Kierbos, and there the farmer grows oranges. And what they do, the farmers, is they dig out big holes in the ground for dams to collect water. And of course, they often do this in the shale because the shale is impervious to water and it acts as a kind of pond. So that's why we end up working on farms a lot, because they've already excavated the sites for us. And the other place where you can dig for these fossils is a roadside quarry. So most of the roads don't have tarmac, and so the roads people dig out the shale from the odd quarry up and down the area, and they basically shove this shale all over the road. So when you're driving around there, you're basically driving over Soom Shale and probably crushing all these gorgeous fossils to smithereens. So it's a bit of a weird setup. As far as is it still being dug, I now have a PhD student, Claire Browning, and she works at the Ezeco Museum in Cape Town. And myself and her are still very actively working some of the localities and finding fossils and so on. So, yeah, it is still being worked on, but not by many people.
Is it protected? In the UK, we have these triple SIs, like sites of special scientific interest, they're called, and they dictate that you can't destroy the rocks without permissions from the government or so on. Is any of that in place in South Africa?
So the sites themselves aren't protected, partly because they are on private land, but you're not allowed to export any of the fossils, so it's protected in that sense. So if you were to go there and find a bunch of cool fossils, you can't just then go and take them out of South Africa. So to collect there, you do actually need to get permission from the South African government, and you get a permit, and then you can actually start digging for fossils. But in terms of special protection, there isn't any other than that.
Is it famous within South Africa? Is it widely known about? Or is it just something that passes everyone by?
Yeah, that's a really good question. So South Africa is obviously famous for some of the world's best hominid sites. And they also have some amazing fossils, reptiles and so on in the Karoo. And I guess if you were to ask most South Africans, they'd know about those, but they wouldn't know about the Soom Shale. I'd like to think that quite a lot of paleontologists have at least heard of the Soom Shale, but your average South African, I don't think they'd be particularly aware of it. Partly because when you're competing against hominids and amazing reptiles, it's quite difficult, and so that's why I think it's perhaps not as well known. And it is quite restricted, just to the Cape Province as well.
How old is the Soom Shale?
So it's been dated by Chitonozoans by a colleague of mine, friend Thijs Vandenbroek, and it's around about 444, something like that, 444 million years old. So that might not mean that much to most people. So just to sort of stick that into context, it's right at the very top of the Ordovician in a time interval called the Hanantian, which is famous for a glaciation, a widespread, severe glaciation.
So where was South Africa at that time in the Ordovician? And was it, I'm guessing, fairly chilly?
Yeah, it was very chilly. So we have really good evidence of this in the Soom Shale. So underlying the Soom Shale is a glacial diamict. So basically, all the stuff coming out of a glaciated landscape, but being deposited in a shallow marine environment. And then the Soom Shale itself, right at the base, has things called drop stones. So these are big kind of pebble clasts. And the way they got into the shale, which is otherwise, super fine grained, is that they kind of rafted on icebergs, which were around ice sheets, and then over the ocean. And then when the ice sheets melt, they drop these stones, hence they're called drop stones. So it was very chilly, but unusually, I guess, the latitude was around something like 30, 35 degrees south of the equator. So the Hernantian, this late Ordovician glaciation, is characterized by having, a chilly icy world at very low latitudes as well.
So what kind of latitude is that comparable to today? Like which kind of country?
I'm just trying to think. So we're at about 52. I'm not sure.
Oh, so it'd be a lot closer to the equator.
Yeah, let me have a look, Dave.
It's fine. We'll just cut to the answer in a short second through the magic of post-production.
So yeah, New South Wales in Australia and South Africa itself. So okay, we can cut to that.
Okay, but even if it hasn't moved a huge amount, well, it might have moved a huge amount, but it's in roughly the same position it was, the same latitude in the Ordovician as it is in the modern times, but the climate, that has changed drastically.
Yeah, I mean, of course, the big thing in the late Ordovician was not only was there this major glaciation, but South America was kind of tucked into the armpit of Africa, so they were kind of joined together. So that was another big change. But South Africa itself hasn't moved that much. So today in the Cape, it's a kind of Mediterranean climate, and then back in the Ordovician, very chilly, glacially influenced, hugely windy and cold. So it's gone from that's somewhere you definitely would not want to go on holiday. Whereas South Africa today, you would definitely want to go on holiday there. It's a wonderful country to visit. Okay,
and what was the depositional setting of the Soom Shale? And by that, I mean, what kind of environment was it? I know you said that it was a load of glacial material being washed into the sea. Was it kind of like a big, empty, shallow basin or something like that?
Yeah, I think that's probably a good picture, actually. As far as, definitely it was marine. So we have fossils which are only found in, truly marine rocks, things like the conodonts and the orthocones. So we know it was fully marine, but it was probably fairly shallow water as well. The rocks immediately below and above it are very, very shallow water. So that also feeds into that idea. So just imagine a kind of, seaway, which is fairly shallow, which may, at least initially, have had ice rafting over the top of it. That's the Soom Shale depositional setting.
So of the sediments that you said were being washed into this shallow sea, you said that they came from glacial activity. So what I remember from geography is that the glacier is kind of like a river of ice that slowly pushes its way down a hillside over thousands of years or something, depending on the type of glacier. But that will like grind up the rock into a kind of fine flour. So how did that get from the mountainside with the glacier to our shallow sea? Did the glacier itself take it and then drop it?
That's a good question. I think there's probably a few routes. So the sediment itself, one of the types of layers that we get is probably just a simple distal turbidite. So stuff coming out from rivers into the basin and being deposited like that. So that's nice and simple. But then we get this other really weird layer that's throughout the Soom Shale, and it's got these kind of clusters in of big outsized grains that aren't drop stones. They're all kind of clustered together. And the size of those grains is exactly the same size as wind-blown dust material is today. This is material that is called loess, which is spelt really weird. It's Loess. Anyway, so the idea is that if you imagine a kind of glaciated landscape, but then as the glaciers are retreating, so the Soom Shale was deposited right at the end or the immediate aftermath of the glaciation. So the glaciers are retreating and they leave this kind of landscape that's been ravished by the glaciers. And exactly as you say, it's all this finely ground material. So the glaciers are going back and the wind blows across these dry landscapes and it picks up this material, this dust, this loess, and then it basically flies out to sea. And of course, as soon as it hits the ocean, it sinks. But there is another sort of aspect to the story, which is really interesting, is that some of the grains that we have are much bigger than you would expect, that the wind would be able to blow in one go. And so the idea here is that the wind picks it up and it kind of jumps across sea ice until it eventually ends out in the ocean and then it sinks. So it's very similar to some areas of Antarctica are today. The McMurdo ice shield, for example, exactly the same sort of processes happen there where big grains kind of jump across the ice and then end out in the ocean. So that's probably what's going on with the Soom Shale as well.
You preempted my next question. I was going to say that sounds pretty rare for a kind of like a rock forming process, because we can all think of big river deltas moving out sand and mud, but there's not very many places I can think of where the wind is blowing dust from glaciers out into the sea. So
yeah,
is it pretty rare to find rocks like that?
Yeah, it is, Dave. But I guess there are two. One is, yeah, for sure, we know it's happening in Antarctica today, and it's probably happening, areas of Siberia and so on. I think one of the biggest problems, though, is that once this wind-blown dust reaches the sea surface and then it sinks down, it's so diluted normally by all the other stuff coming in. So the stuff from rivers, deltas, turbidites and so on and so forth, you can't really identify it because it's just a massive mixed bag of sediments. But for some reason in the Soom Shale, you can identify it because it stays in it's kind of clumped together in these clusters. And so therefore we can read the signal more clearly than you would in any other sediment where this might be happening, but you just can't see it's happened.
Okay, so we're going to have to explore this. How did dust landing on the surface of the sea end up in clusters?
Yeah, brilliant. So this is actually the one of the main topics of my PhD student, Claire, who's working very hard on this. Looking in super detail at these clusters, how many grains are in each cluster? Does it change up through the sequence? How big are the grains? All sorts of patterns that she's looking at. So we have two theories. The leading theory is that if you imagine this dust landing on the surface of the ocean, it's actually super nutrient rich. It's containing a lot of iron and perhaps other elements. And it leads to an algal bloom. So it basically is very nutrient rich. You have an algal bloom. And what we've seen is that these clusters of grains are kind of wrapped in organic matter. So the idea is that the grains land, they make the plankton, the algae, proliferate, and they kind of basically get wrapped in almost like an algae cling film. And then They sink to the seafloor like that, and then that's why you get these clusters. The other theory, possibility, is that the grains are somehow still coming in a benthic way along the seafloor, and then somehow they're getting wrapped in algae that's living on the seafloor. But our preferred scenario, and the one that seems to fit most of the evidence, is the first one, where they're kind of landing on the sea surface and they're fertilizing the ocean, lots and lots of algae bloom, and then they kind of get stuck to that algae and sink.
Okay, and that's how we're getting all of our nice clay minerals to the sea floor. But living in the area at this time, we have all of these different animals, all of these different organisms. That clay eventually ends up replacing some of the tissues in those animals. How does that work?
Yeah, again, this is a good question, because I guess when I was a PhD student and I was looking at this, I was pretty confident I'd figured this out. And now I'm a lot less confident that I got it right. But basically, you can see in the Soom Shale that a lot of the organic matter has been entirely replaced by clays. And the clays are able to do this with a high degree of fidelity. So we have fibres where there are muscle fibres, and those fibres are like 5 microns across. So they're really fine. You know, the detail is beautiful. The eurypterids, they have gills, and every single kind of gill lamellae is reproduced in clay. How this happens is a bigger question. Clays and organic matter are known to be have quite a high affinity for each other. So they have various charges on their surfaces, and they kind of like to get it together. And so my idea as a PhD student was that that's exactly what happened, that there were these charged surfaces, and the clays kind of organised themselves onto the decaying tissue and eventually replicated it. But now I think that may have been going on, but I also think some of the clays may have grown much, much later, because the Soom Shale has been cooked up a little bit, not much, but just a little bit. And it's possible that some of the clays have reorganised themselves during that sort of gentle cooking.
And that's all part of the taphonomic process. Like, we have the replacement of tissues with clays, and then the clays are also changing with time.
Yeah, definitely. Yeah, the clays are changing with time. So this is one of the really interesting things, but super challenging, I think, for taphonomists, particularly when you're looking at how organic material is changed through time to stay as organic material, or as organic material is replaced by mineral material. Is trying to kind of work out what was weathering, what was metamorphism or slight cooking, and what was happening originally, you know, soon after the animal died. And disentangling all that kind of evidence is a real challenge.
Yeah, I bet. I'd rather you than me. So you've mentioned a few different animals and also organisms throughout the course of this interview. One of them was vertebrate thingies, conodonts, like fishy things, and then sea scorpions, which are arthropods. They're all made up of, well, they're all different in terms of their anatomy and composition and stuff. Are all the fossils preserved in the same way? Do they all interact with the clays in the same way? Are they all replaced by the same clays, or are there differences between all the different animals and groups?
Yeah, there are differences. It's a good question. I think, so very broadly speaking, one of the weird things about the Soom Shale is that the material that was mineralized in life, so for example, calcite of trilobite exoskeletons, calcium phosphate, so apatite, like your bones and teeth of the conodont teeth, and also in some of the brachiopod shells. And the orthocones, big mollusks, they would have had probably an aragonite shell. All of that stuff's gone. So all of the bones and teeth and shell, the stuff that you normally get in the fossil record, is basically dissolved away. You still get impressions of it, but there's no actual mineral there. And then the stuff that usually goes, so the gills, the muscles, the eyeballs, the skin, the tissues, the sinews, all that kind of stuff, that's actually preserved, usually in clay, but also quite a lot in organic matter. So, and there doesn't seem to be a huge pattern between, okay, all eurypterids are preserved like this, or all musculature is preserved like that. It's quite a mixed pattern, but it's completely weird.
That does sound weird. If we take our giant squiddy nautiloid things as a case, so they have a large conical shell that you're saying is not preserved. Do you find like a negative space where it used to be?
Yeah, it's you get really amazing features on the shell. So the shell, you can see that the shell is dissolved, and sometimes it's even kind of got crinkles and wrinkles on it. So these particular animals probably had something called a periostracum, which is an organic layer outside of the shell layer. So the shell layer dissolves away, and then the organic layer kind of, if you imagine it kind of gently floating to the seafloor and wrinkling, a bit like a piece of material would if you were to sort of lay it down on the seafloor. So the shell is gone, but in the nautiloids, you do get their radula preserved. So the radula is like this tongue structure, which has got multiple rows of teeth that they use maybe for predatory reasons. And you get them today, in octopus and other cephalopods. Now, they're not mineralized in life, but in the Soom Shale, they are preserved, but they're entirely moldic. So it's like the impression of all the features in 3D in the sediment, but without any material there.
Wow. That sounds fantastic. Like some of the things that you've said, the kinds of things that you get preserved, it sounds unbelievable. Like it's completely the opposite of what you'd normally expect. So just how good can this preservation be? What's the highest amount of detail we can get?
Yeah, that's a good question. So I think clay is quite good at replacing soft tissues, if it does, because it's a very fine kind of mineral anyway, isn't it? It might have been colloidal clays, so clays that are kind of just knocking about in the water, super, super fine, and they only settle when they have certain charges or they're attracted to organic matter. I think there is a limit, though. I've never seen anything in the Soom Shale that's better than, say, 5 microns in detail. That's pretty good, but there are other deposits which do a lot better than that. And calcium phosphate, when that replaces soft tissues, people have suggested, Dave Martill, for example, in Portsmouth, and Phil Wilby at the British Geological Survey, they've recorded cell nuclei and details like that in calcium phosphate. So it can get much better than in the Soom Shale. But, the thing about the Soom Shale is the preservation is gorgeous, for sure, but it's kind of the setting that's so weird, and it gives us this really unique view on life in a very cold zone, way back at the end of the Ordovician, a critical time, because we just had the Ordovician, mass extinction in the Ordovician, and this is almost just in the immediate aftermath of that. So we're seeing this unusual setting. It's an icy world. We're seeing it at a strange time, just after a mass extinction. The preservation is really weird. Some of the animals are like holdovers from the Cambrian. So we have these things called neuroids, which are very famous from the Burgess Shale and the Chengjiang. They're in the Soom Shale. So it's a bit of an oddity, but nonetheless, it's really interesting because it gives us a unique view on a strange environment.
Okay, well, let's explore the taxa of that environment. What are some of the most commonly preserved animals there?
So actually, the fossil that you find the most commonly is also one of the weirdest, and also I have no idea whatsoever what the hell it is. So you find them a lot. They're if you imagine going up to a blade of grass and just cutting off the top centimetre of a blade of grass, and then getting lots and lots of those and scattering them over the seafloor. That's kind of what they look like. They're little axes, little spiky axes, and they're called Siphonasis. And again, they were written up as a plant, but I don't think they're a plant. In fact, I have no idea what they are, but they're everywhere. And their morphology, I've seen nothing like it anywhere else in any of the other fossil lagerstätten through time. And they're very weird. And they don't have any orientation, so it's hard to see exactly, did they come from a bigger animal? Are they like little spines or spikes off a huge animal? Or are they, something, an entire entity in and of themselves? I've no idea, but they're the most common fossil.
That's astounding. Are we going to be able to get a picture of them?
Yeah, I should
right.
Send you one of those. Yeah, no probs.
Listeners, in the comments, what do you think these are?
Yeah.
Yeah, we might get our answer. Someone might recognize it. Who knows?
I would be very grateful because I'm completely stumped.
Wow, that's fantastic that there's just such a giant mystery.
Yeah, and there's quite a few fossils actually. I had a PhD student called Rowan Whittle, and she now works actually in the British Antarctic Survey, and she's a fantastic paleontologist. And her job as a PhD student was to look at all the enigmatic fossils from the Soom Shale, so things like this, and then a whole host of other things. And she was brilliant. She was able to identify Lobopods, for example. So we had these really strange kind of sets of repeated segments with little hooky things on. And she worked out they were Lobopods that had kind of twisted round. And she was able to identify quite a lot of the fossils that were a bit weird and wonderful. But even Rowan couldn't identify the Siphonasis. So it's still a mystery.
Well, what are some of the organisms that we might be more familiar with then?
So I guess it's probably the arthropods, so the sea scorpions, the eurypterids. They're really beautiful. They're about 10 to 15 centimetres long, and they're wonderfully well preserved. You have their food tract and their gill lamellae and their muscle blocks for all of the appendages. You also have these neuroids that are, typical in the Cambrian lagerstätten. What else do we have? We have Lobopods. Conodonts, I guess, are the most famous fossils from the Soom Shale. So these are primitive vertebrates which have a kind of tooth set in their mouth, but the rest of their body is kind of an eel shape with big muscle blocks. And we think they're a bit more derived than hagfishes and lampreys, if you're familiar with those. They're the most primitive living vertebrates, the hagfishes and lampreys, and the conodonts sit just a bit up crownwards from them. And we have things called Skelecodonts, which are kind of annelid worms, which probably sat in the sediment and preyed upon creatures. We've got brachiopods. Lots of people know brachiopods, a few different types of brachiopods. So there's a whole array of fossils, but it's not incredibly diverse. It's not as diverse or anywhere near as diverse as, say, the Burgess Shale or the Chengjiang. It's definitely quite a restricted fauna. But given the fact these fossils were coping with the aftermath of a mass extinction and an icy conditions, then it's kind of not surprising, I guess, that it's not as diverse as other deposits.
Do you think there'd be more diversity if you were to excavate a whole lot more? Because it sounds like there's a whole load more rock down there. Do you think there's still new taxa, new animals to be found?
Absolutely, yes. So if you think about some of these deposits, so for example, the Chengjiang has many, many people sitting on the deposit day in, day out, collecting those fossils. The Burgess Shale, much less so. It's a really tough deposit to collect at because of the conditions up in the Rocky Mountains. Nevertheless, from 1963 onwards, every single year, more than 10 people have collected at that locality. So the Soom Shale, it's been myself, lucky me, and then Dr. Hannes Theron, Professor Richard Aldridge, my two supervisors, Rowan Whittle, my PhD student, and Claire Browning, and that's it pretty much. So I think you're right. If we could excavate more and get more people, then we'd probably find more.
People, this is on a vineyard. You can drink wine in the sunshine and dig.
Yeah, I'll tell you one thing though, the bad side about collecting in the Soom Shale is, oh my word, you have to be so patient. So, we had a standing joke and a kind of bet on who went the longest without finding anything. And you can go days and days and days and days and days and find a brachiopod. It is hard work, and you really have to know which layers to look in, because you can chop an awful lot of shale and find absolutely nothing for days and possibly weeks. So it's really tough to excavate the material there. And also the shale, when it rains, it kind of almost melts. So you've got to get the weather just right and so on and so forth. So it's hard work, but yeah, I wish I had an excavator.
Well, maybe someone with a spare excavator's listening. But it sounds like all the effort is completely worth it. And when you take into account some of the fossils that have changed how we, view and different fossils. So, for instance, the conodont. Can you talk us through the significance of the discovery of the conodont fossils from the Soom Shale, like from what we thought they were to what we discovered?
Yeah, sure. So for, I don't know, something like 150 years, paleontologists have used these little phosphatic sort of spiky things that come out of sandstones and limestones to date rocks, and also to tell us how much gas and oil are in the rocks. But nobody knew what animal they belonged to, because they were just little isolated spiky things. Sometimes you got a whole set that kind of worked together, but nobody knew what the animal was. It's a kind of long story, but to cut it short, there are then only 4 places in the world where not only do you get the little spiky elements, but you actually get the soft tissues preserved of the animal. And that's the critical thing, because the soft tissues being preserved helps us to determine what the animal was and where in the animal the spiky bits were and what they were doing. And the best records actually come from Edinburgh in the Carboniferous, the Granton shrimp bed. And here, conodont animals were discovered in the 80s. And this big enigma of conodonts was kind of finally solved, that they were some kind of vertebrate, because they have an eel-like body, and they have a caudal fin, and they have a notochord, and they have eyes. And the spiky bits are actually the teeth, and you know that because you can now place them in the mouth. And then in 1994, actually, we discovered the conodont animal in the Soom Shale, and this was a monster. So most conodont elements are about 1 millimetre long, and the ones in the Soom Shale can get up to 2.5 centimetres long.
Oh.
Yeah, they're another weird thing about the Soom Shale is the size of some of the animals is off for what we normally get. And the conodonts are giants. And the conodont animal that we found there, it wasn't complete, but if it was, it would have been about 40 to 50 centimetres long, whereas the Scottish ones are only about 4 centimetres long. So 10
times bigger?
Yeah, so they're real monsters. They're 10 times bigger than, most other conodonts. And what we found was the trunk, the muscle blocks. We found probably a liver preserved, but the eyes were very important, because when we put the eyes under the scanning electron microscope, we saw that they had extrinsic eye musculature. So this was another key characteristic that allowed us to place these animals correctly onto the tree of life as being kind of primitive vertebrates allied to the hagfish and the lamprey. So they're basically the earliest vertebrate to have a mineralized part to their skeleton, in other words, their teeth. And so that's why the conodonts from the Soom Shale and from the Granton shrimp bed in particular are very important to our understanding of vertebrate evolution.
Yeah, that sounds like a fantastic discovery. Are there many of those conodont animals, these giant 50-centimetre ones?
No. So in all the years I've collected at the Soom Shale, we've collected as a team, we found two. The best one is much better than any of the others. Now, we do get a lot of eyeballs, funnily enough. So a lot of the mouth parts, these spiky elements, come with their eyeballs. So the eyes are very well preserved, and they're big as well. The eyes are very big. So we get a lot of eyeballs, we got a lot of teeth, and then one or two actual animals. And that animal was found as kind of a nice story. So it was the last day of collection, and we'd been on a new locality, and it was a complete nightmare. The rock was rubbish. It wouldn't split very well. It was really hard work. It was really, really hot. It wasn't a vineyard, so, another morning. And, we were all tired. And I, for a joke, kind of scratched in a pretend conodont animal using my chisel onto a piece of the shale and chucked it at Dick Aldridge and say, "Hey, I found a conodont animal." And he was, yeah, ha, ha, ha. And then literally about 3 splits after that, I did find a conodont animal. So when I said to him, "Oh, I found a conodont animal," I think, he didn't believe me till I showed it him. And then he was over the moon, because Dick Aldridge is one of the world's leading experts on conodonts. So it was fun times.
I have been guilty of doing that myself, scratching in what I want to find into the surface of the rock. But the only victim of that is often myself, because I'll be going through some of the rocks just lying around on the surface, and then all of a sudden my eye just catches just exactly what I was looking for, and oh wait, no, it was me that scratched that in.
Yeah.
And then I learned to just throw it away a bit further. And I've actually had it where years later I've discovered something that I'd scratched in myself. So
got all excited.
Yeah, a lesson for everyone learning: don't do that. You'll just disappoint someone else or yourself eventually. Yeah, it was a real shame that we didn't get Dick Aldridge on the show. We'd had an episode scheduled with him for years, but as his health had declined, we just couldn't get him on. So it's a shame that we never got to speak to him. But still,
he would have enjoyed it. And Dick Aldridge is an amazing person and paleontologist, and we miss him.
So we've said about the public appreciation of the Soom Shale and that it's not very well recognised. Do paleontologists and the academic community recognise it a bit more?
Yeah, I think so. I think it's fair to say that. I mean, look, it's not a Burgess Shale. It's not a Chengjiang. It's a bit unique and a bit odd and a bit weird, but some of the fossils are incredibly important. They have told us a lot about paleobiology. They've told us about the range of different creatures. It's incredibly hard to find the fossils, and even if you know what you're looking for, sometimes they're quite hard to see, even if they're right in front of you. because of the nature of them. It's kind of grey on grey. But I like to think, people are interested in the Soom Shale. We wrote a paper, the whole team, a couple of years ago in the Journal of the Geological Society, just kind of summarising it. And that got a lot of downloads. So I was quite pleased to see that. So it's a really important deposit for its time and its place and its context.
What are some of the questions left unanswered about the animals, about the fossils in the Soom Shale, and about the Soom Shale itself?
Okay, well, there are still quite a few animals I have yet to write up. So one is a fish. So there are naked jawless fishes in the Soom Shale, which are a bit weird as well, actually, because they're mostly preserved. You can mostly see them because of their eyes and their livers. And the rest of the animal is very, very faint, but you can see a big kind of gill basket. So we think there's some kind of an aspid type fish. So that will get written up soon. We've also found a huge multi-segmented arthropod. I've now kind of figured out what that is, so watch this space on that one. What the hell is Siphonasis? Still don't know, and there are quite a few fossils like that that are still enigmatic. I'd like to know, is it wind-blown sediment? Did the wind-blown sediment fertilise the oceans? How did that happen? And also the taphonomy. I still think there are quite a lot of unanswered questions there. We've recently found some fossils which are beautifully well pyretized. So that's another kind of mode of preservation that we need to understand. And I'd love to look at the eyes and see if there's melanin in the eyes, because we have these big black eyes associated with the conodonts. Is that melanin? Is that some form of retina being preserved? So there's stacks still to do.
Well, hopefully we'll get lots of people interested and you'll have tons of PhD applications from this. So looking back on the interview, the thing that I will probably take away from this is that we have a lot of fossils that are just a bunch of eyeballs and livers being preserved, and you just would not expect that at all from a fossil. It's normally shells and teeth or whatnot. So yeah, just this association of eyeballs and things. What would be the one thing that you would like people to take away from this interview about the Soom Shale?
I guess something even more broadly than the Soom Shale is that, when you're a paleontologist and you're trying to understand the history of life, I think it's really important to think about the deposit. And, we've done that in this interview. You've asked me a lot about the setting, about the climate at the time. You've asked me about the sedimentology, the whole kind of picture. And I think if we can understand all of that together, then the fossils become even more powerful in understanding the evolution of life.
Okay, well, thank you so much for coming on the show today.
You're welcome. Thanks. It's been fun.
Paleocast was brought to you by Dave Marshall and Liz Martin Silverstone, with contributions from Tom Fletcher, Vish Venkat, and Elsa Pancharoli. Music was composed by Patrick Kendall Smith. Paleocast was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on funding from you, the listeners. So, if you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programs, and follow us across social media platforms to get all the latest news. Finally, if you enjoy our podcast, then please explore all of our video content on YouTube and follow our other projects, the Virtual Natural History Museum and the Paleocast Gaming Network.